Hi students, now let's discuss about the isomerism in alkanes in this lecture. But before, I would like to highly recommend you that you first go through the introductory video of about the isomerism, right, and then come to this one. I have a couple of videos on the isomerism in organic compounds, right? So you just first go through those introductory videos of the isomerism and then come to the isomerism in alkanes. Okay, so alkanes, we know that the general formula of alkanes is CnH2n plus 2, and these are the saturated hydrocarbons. Now regarding the isomerism, we find there are two types of isomers in alkanes. One is a structural isomer, another is the stereoisomer. And among the stereoisomers, there are two types: conformational and configurational. Configurational isomers, there are further of two types: geometrical and optical. I have a couple of videos on the isomerism where I have explained how a structural isomer is different than stereoisomer and how a conformational isomer is different than configurational. What are the conformational and what are the configurational isomers, geometrical and optical? We have I have taken these topics separately. I would like to you go through those videos and then come to this one, right? Today our topic will be isomerism in alkanes. Alkanes, they show normally two types of isomers. One is a structural isomer and the second one is a conformational isomer. Correct? So structural and the conformational isomers, these are the two topics that we will discuss here in alkanes, because we find with alkanes two kinds of isomers commonly. Number one is the structural isomer, very common, another is the conformational isomer. Okay, so let's first start with the conformational isomers. Sorry, the structural isomers. The structural isomers, we know here the structure of the two compounds is different, but the formula is same, right? So like, let's suppose we take the molecule like this: CH3, CH2 and the CH3. This is propane, right? In this one there are three carbon atoms here. Okay, if you look at this hydrogen here, what is this one? This is the primary carbon. This one is the secondary carbon, and this one again is the primary carbon, right? If you attach a group, suppose here on the primary carbon, if you attach if you replace, suppose here, the hydrogen by a methyl group, right? So what you will get, you can get the molecule like this: CH3, CH2, CH2, CH3. I simply replace the hydrogen from the primary carbon and I got the butane, right? This is N-butane. This is called N, the normal butane. But if I replace the hydrogen from the secondary carbon and then I put the methyl group there, so I'll get CH3, CH, single bond, CH3, and this is the CH3. This is called isobutane, right? This is an isobutane, and you can also call it as a 2-methyl 2-methyl propane. Now with these two compounds, they have the formula same, right? The formula is same. When you find how many carbon atoms are here, carbon atoms 4, C4 and H10, right? Same formula here, and here also the C4H10. Two compounds with the same formula, but the structure is different, right? Okay, the structure is different. Okay, one is a chain molecule, a linear molecule, and is a branched molecule, right? This type of a isomerism, this type of structural isomerism is called as a chain isomerism, right? Because we have different kinds of structural isomers, and if you have a molecule in different structures, right, linear molecule and then the branched one with the same formula, you get this is called as a chain isomerism. So that means the isoalkanes actually they exhibit the structural isomers, and among the structural isomers, which type? It is the chain isomerism. As I said, I highly recommend you to go through the videos of my isomers, the isomerism, the hydrocarbons. I have explained the different types of structural isomers there also. Over here, this is a chain isomer, right? Fine. So that means alkanes, they show the chain isomers. You can draw different structures for the same formula, right? And the name is also different, right? You can see this is the N-butane, normal butane, or simply you can say butane, while this one in IUPAC nomenclature, this is 2-methyl propane, right, or isobutane. The propane itself cannot show the geometrical isomerism because it only has 3 carbon atoms. We see the geometrical isomerism, this structural isomerism. This is only possible when you have molecules containing more than 4 carbon atoms, right? So that means this type of a structural isomerism is not possible with the methane, which only has a 1 carbon, or the ethane, CH3, single bond CH3, or the propane. So these 3 molecules do not show the this structural isomerism. Compounds containing 4 carbons or more show the structural isomerism in alkanes. And we can try and draw a number of different structural isomers for the different molecules, and we can find how many structural isomers are possible. For the butane, actually, for the C4H10, there are only 2 structural isomers, these 2 structures which are possible, correct? So now if you have suppose the C5 molecule, right, if you have suppose the C5H12, okay, C5H12, there are 5 carbon atoms, correct? So the 5 carbon atoms, let's try to draw the structure. I think it will be like this: 1 2 3 4 5, which means this particular one, it means 1 carbon, this is 2nd carbon, this is the 3rd carbon, this is 4th carbon, this is the 5th carbon, right? This is a bond line representation of alkanes, right? Here it means this is the C5 carbon, this is actually the pentane, okay, this is a normal pentane. Now if I take suppose here the 4 carbon atoms like this, and I put a methyl group here on the 2nd carbon, now this one is different than the first one, right? This is another structural isomer. I'm taking 1 methyl group from here and put it on the 2nd carbon. Now you got what? This is the 2nd isomer of the same formula, C5H12, okay. This is pentane, this one is pentane, while this one is isopentane, another structure, right? Another structure. Or you can say this is the 2-methyl butane, right? 2-methyl butane, the 2 compounds with the different names actually in terms of IUPAC nomenclature system. Or I can draw one more structure. Suppose I have 3 carbon atoms like this in the linear shape, then take 1 carbon here, another carbon here, right? This is another totally different structure. This is called Neopentane, right? This is the Neopentane, or you can call it a 2,2-dimethyl propane, right? 2,2-dimethyl propane. These 2 structures actually, these 3 structures, they have the same common, they have the same formula, but the structure is different, right? And these are the structural isomers of pentane. Similarly, you can draw the structural isomers of C6, C7, C8, and you can find how many different types of these structural isomers we can have for a molecule. And there is no particular formula to calculate the number of structural isomers, the structural isomers of an alkane. We have to just try to draw the different molecules, right? So there is no particular formula actually to count the number of the structural isomers for a particular alkane. Like for the butane, there are 2, and for the pentane there are 3 isomers, right? There are 3 structural isomers possible, right? Okay. For the C6, you know, if you try for the C6H14 molecule, for this one I think there will be the 5 structural isomers, right? For the C7 H16 there will be the 9 structural isomers, right? Like that. So you can just try to draw the different structures of the same formula, and they have the different names actually, right? The name of the compound will be totally different. And now these are the molecules having the same formula, but the structure is different. Now let's try to let's take the another important, very important topic, that is the conformational isomers. What are the conformational isomers? Okay, see, in alkanes we know there is a carbon-carbon single bond. Okay, there's the carbon-carbon bond that we find, that the sigma bond, because single bond is always a sigma bond, and it has other groups attached to it, right? The carbon has other groups attached to it, and around a single bond there is free rotation possible, right? So there is free rotation possible, and because of that rotation, you know, the relative position of the groups attached to this to these 2 carbon atoms, they get different, you know, relative positions. You know, when suppose we have a molecule like this, suppose this is ethane, and if there is rotation around the carbon-carbon single bond, due to that you get different types of positions, where suppose in this particular one the 2 hydrogen atoms are slightly closer, and if you rotate this one around the single bond, carbon-carbon single bond, you get a new arrangement of atoms, right? So arrangement of atoms around the carbon, relative position of the atoms here, that will be different. Suppose here in this position the hydrogen atoms are slightly closer, and if you rotate it here, now you know the 2 carbon atoms will have a little bit like this, right? Okay, if you simply rotate it by around a 60 degrees Celsius, what you get a different conformation, right? Okay, now this rotation around the carbon-carbon single bond, due to this rotation you get different isomers, right? You get different isomers, we call them as conformational isomers, and we'll see how how many different types of conformational isomers are actually possible. And these conformational isomers are possible due to the rotation around the carbon-carbon single bond. If there is no rotation, you cannot have a conformational isomers, right? So it is because of the rotation around the carbon-carbon single bond that we find one isomer changed into the second, and the second will go back in the first one, right? Okay, you can see the second structure will go back to the first structure, because the energy difference that we find here between the 2 molecules, the energy that we require here for this kind of a rotation around the carbon-carbon single bond is quite low, and that energy is available at the room temperature, right? Now look at this one, right? If we let's take an example of a ethane CH3 single bond C3, a very common and a very simple alkane. Around the carbon-carbon single bond there is rotation, free rotation is possible, okay, because the energy requirement for this is quite low, and that is available at the room temperature. And if you have if you look at this one, this is the carbon number 1, this is the carbon number 2, this is the Sawhorse projection, how we show the how we can show the ethane molecule in the Sawhorse projection, right? Okay, as if you are looking at the molecule from the top, and you are able to find the 2 carbon atoms, right? The length between the 2 carbon atoms, the bond length completely visible to you, and you can see this is the front carbon, suppose this is the back carbon, and these are the 6 hydrogen atoms around it, right? 1 2 3, these are the 3 hydrogen atoms here, and these are the 3 hydrogen atoms to the second carbon. Now see what we find between these 2 hydrogen atoms over here, they are eclipsed actually, right? These are eclipsed. If you look at this molecule from this angle, what you'll find, you'll find that this hydrogen actually is in line with this hydrogen is in line with this one is in line with this. And if you give any kind of a rotation to the molecule, suppose if I rotate the molecule around this carbon-carbon single bond about the 60 degrees only, okay, let's give the rotation around this around the carbon-carbon single bond by about a 60 degree rotation. Now what will happen, suppose if I rotate it now, for example, this hydrogen will shift here, this will shift here, and this will shift here. And now what you get the Sawhorse projection, right? You know, keep the front carbon here intact without changing its position, right? Give the rotation to one of the carbon atom, right? If I rotate the back carbon here, now what I find, you know, the hydrogen shifts over here, this hydrogen shifts over here, this one over here, and you get now different conformation, right? Now the arrangement, the relative position of atoms is here different, isn't it? The relative position of atoms is different. Now the hydrogen atom, this one is not in line with any other hydrogen atom, correct? Okay, so basically this hydrogen atom is present in between these two, right? And this one is present in between these two, right? So this is not an eclipsed one, right? This is called what we call as a staggered one, right? So this is the eclipsed state, eclipsed conformation. This is the staggered conformation, right? In the eclipsion, there is you know, eclipsion between the groups, right? They are actually in line. Here in this one they are not in line. The distance is slightly, you know, more between the two metal groups, and that's why the eclipsed state is relatively less stable than the staggered. So staggered is more stable one. Staggered is a more stable conformation than the eclipsed one. Okay, and this is actually how we represent the ethane molecule in the Sawhorse projection. We have a one more method actually to express, you know, to show the conformational isomers, right? Not only the Sawhorse projection, we can show the conformational isomers of ethane molecule in another projection called the Newman projection, right? In Newman projection, how we represent it? Okay, we take, suppose, the dot, okay, which means the front carbon here. Okay, in the Newman projection, as if you are looking the molecule from here, from this angle, and this is your front carbon. Now I represent by the dot, and the back carbon here, right? This particular carbon, I represent it by the circle. So the dot is the front carbon. Now front carbon has three hydrogen atoms. One is like this, another is like this, another is like this, right? So here you get the three hydrogen atoms. For the back hydrogen in the eclipsed state, this hydrogen is in eclipsion with this one. So therefore, for the back carbon, which is represented by the circle, that also has the hydrogen atoms, but this hydrogen and this hydrogen will be under eclipsion, right? Same thing will happen over here. There is one more hydrogen atom, but the hydrogen atoms are under eclipsion, right? So there is one more hydrogen atom over here. Now this is the eclipsed state, correct? This is the eclipsed state of the ethane molecule. Now this is called as Newman projection, and this is the Sawhorse projection. You know, both are eclipsed, right? This is also eclipsed, and this one is also eclipsed, correct? So this one is also eclipsed, and I can draw now the staggered, you know, the staggered conformation also in the Newman projection as well. And how we do it? Again, same thing. Front carbon by the dot, by the, you know, by this center, right? And around this I'll put a circle which represents the back carbon. Okay, so sorry, this is not a perfect circle here. Okay, so front carbon, it has three hydrogen atoms, isn't it? So three hydrogen atoms here, attached to it, and now it's different than this one, right? As if I am giving rotation here. Okay, I am giving rotation, suppose, to the back carbon. This, you know, 60-degree rotation by how much? It will move over here, right? This one will move over here. This one will be here. That means this hydrogen atom actually is present in between these two hydrogen atoms. Now this is not an eclipsed state, right? Okay, this is not an eclipsed state. This is the staggered one, correct? And here what we find that the hydrogen atoms are a little bit away from each other, so repulsion will be less, and that's why this is more stable, correct? These are the two conformational isomers of ethane molecule, right? Again, the same thing here. You know, this is the Sawhorse projection. How we represent the Sawhorse projection? Okay, what is this one? This is actually an eclipsed state. Sorry, this is the anti, right? The staggered, right? Okay, this is called as a staggered one, right? And here this is an eclipsed one, right? This is an eclipsed one. Okay, and this is actually how we represent the Newman projection, and this is in the Sawhorse projection. And the energy requirement, you know, for this one, for the conversion of the staggered to the eclipsed state, right, it is done only by the 60-degree rotation, but the energy requirement is very less, only about 12.5 kilojoules of energy, you know, 12.5 kilojoules of per mole of energy is required for this conversion. This is, you know, available at the room temperature, and that's why the molecules keep on changing. You know, this process, these isomers are something which we call them as momentary isomers also. Why? Because they exist only for a fraction of the time, you know, and we cannot separate these molecules, these isomers as well, because they get interconverted even at room temperature. Even at a very, very low temperature, they get interconverted. You get the eclipsed converted into the staggered one gets back converted into the eclipsed one again by 60-degree rotation, right? Isn't it? Only by the 60-degree rotation. Okay, so let's try to find the how the energy level diagram will look like. Suppose this is the ethane molecule, right? This is the carbon one, this is another carbon, these are the hydrogen atoms here attached to it, okay? And now can you just guess what kind of is it a staggered one or the eclipsed one? Okay, is this one a staggered or eclipsed one? And how can I represent in the Newman projection, right? I think I'll be able to represent like this. Okay, now this is the front carbon, this is the back carbon. Okay, what is it? What is this one? Yes, this is not the eclipsed but staggered one. You know, in between these two hydrogen atoms you are having the hydrogen, right? These are not, there is not an eclipsion. Okay, so that means if I show the hydrogen atoms like this, these are the front hydrogen atoms, the back hydrogen atoms will be like this. So now this is what? This is the staggered conformation. Okay, if I give a rotation around 60 degrees, you know, 60 degree, right? So let's suppose I rotate the back carbon by 60 degree. So then you get what? You get a eclipse state, right? So now there will be the eclipsion between the front and the back carbons, right? All the hydrogen atoms will be under eclipsion. And if I give further 60 degree rotation, again what you get? You know, first one is the staggered one, and now this is the eclipsed one, and now what you get? You again get the staggered one, right? Again get the staggered back. So total rotation of 120. So that means if you have a staggered one and you give a rotation around 120 degree, right, 120 degree, that means what? Again the staggered, right? Again the staggered. Okay, fine. So let's see the energy level diagram. Look at this one, right? This is the potential energy here, and we see that the staggered one is the staggered one here. This is more stable than the eclipsed. In the eclipsion there is a, you know, these two hydrogen atoms are under eclipsion, these two are under eclipsion, these two are under eclipsion, right? So if you have an eclipsed state and we give a rotation of around 60 degree around it, right? So we give a 60 degree rotation around it. What do you get? From staggered, from the eclipsed you get staggered, and again 60 degree rotation you get eclipsed, right? And eclipsed, then the staggered into eclipsed. So this is how they interconvert, right? Okay, so another point is the angle actually, right? The angle between the two atoms that we find, we call that as a torsional angle, right? Okay, this is the torsional angle. Okay, so when the torsional angle, or we also call it a dihedral angle, right? Dihedral angle or the torsional angle. Here the torsional angle is 0, right? So the torsional angle is 0. That means if you have two carbon atoms and they are under eclipsion, right, the dihedral angle or the torsional angle is 0, right? Okay, fine. Now these are the conformational isomers of ethane. Now let's discuss about the conformational isomers of propane. In the propane, we know the formula is CH3 single bond CH2 single bond CH3. Now let's discuss about the conformational isomers about the C1 and the C2. Right, so if we have the two carbon atoms, suppose I have this is the back carbon, this is the front carbon. Now suppose this is the front carbon and let's suppose this is the back carbon. Okay, the front carbon has got 3 hydrogen atoms there, right? Hydrogen atom is here, hydrogen is here, and the hydrogen is here. Now the back carbon, it has say 2 hydrogen atoms, and let me draw the staggered one first. Okay, and let's say this as a methyl group also, right? It has 2 hydrogen and 1 methyl group. So the only difference here from the ethane is that we have a methyl group here. In the ethane, it was having a hydrogen. Now again, if I rotate it by 60 degree, what you will get? 60 means what? You get it over here. Okay. So now what you get? Eclipse state. By angle of 60 degree, right? By a rotation around the 60 degree, now you get an eclipse state. This is an eclipse state, correct? This was the staggered one. Okay, this is the staggered one, and this one is eclipse. Again, a one more 60 degree rotation. Okay, let's keep the front carbon there at its own position. We do not change the front carbon. Let's change the back carbon. You know, you can do the other way also. You can rotate one carbon and fix the next one. Suppose if I fix the back carbon, I can rotate front carbon also, right? That's not a problem. So we can do it with the other way also. So let's have hydrogen atoms here for the front carbon. Again, a rotation to the back carbon. What do you get? Again, this is what? This is a staggered one, right? Again, this is a staggered one. It's the same thing. Again, a rotation around 60 degree. What do you get? You get the eclipsed one. I think this should be very much clear now, right? Now you get the methyl and the hydrogen here. Okay, and then the hydrogen. So staggered by rotation of 60 gives eclipse. Staggered by the rotation of 120 total. You know what is the total rotation in here? 120 degree. That means if I rotate a staggered one by 120 degree, you get again the 60. You get again you again get the staggered one, right? If I rotate the staggered by 180 degree, right? By an angle of 180 degree, what do you get? You get again, you get the eclipsed one, right? So staggered by the rotation of 60 gets eclipsed. Staggered by the rotation of 180 again get eclipsed, right? Fine. And among the stability, which is more stable? Staggered is the more stable than the eclipsed one, correct? Right. So that means if we try to draw the energy level diagram, right, in the propane, so staggered one is the most stable one, so that is this one. Staggered one is the most stable one. Eclipsed is this one, right? This is the eclipsed, okay, and this is the staggered one, right? Here the energy difference is how much? 14.2, okay, 14.2. Again, this is small amount of energy, and you can get it from the room temperature, okay, and that's where the staggered changes into the eclipse. And this is, suppose if you have an over here, what is the angle? Suppose we have the staggered one. If I further rotate it by how much? If suppose here in the staggered one, I rotate it around 60 degree only, there is a change in the 60 degree angle only, you get the staggered into the eclipsed one, correct? and again you give further 60-degree rotation. What you get? You get then again the staggered. You further rotate it by the 60, further 60. Okay, so what you get? You get the eclipsed one, right? This is the eclipsed one, this is the staggered one. Okay, fine. If we compare the the energy difference between the staggered and the eclipsed one for the ethane molecule, right, for this one, right, for the ethane and the for the hydrogen atoms only, if there are only hydrogen atoms, for this one to rotate here from low energy to the higher energy, right, is how much? About 12.5, right? This is only 12.5 kilojoules of energy. But if you attach a methyl group here, right, suppose if you attach a one methyl group here, like in the propane, the energy requirement is not 12.5, that is slightly more than 12.5. However, how much? That is 14.2, right? Why is it so? Because we are actually replacing a hydrogen which is a little bit lighter, right? That the methyl is a bulky group. Okay, so because of attachment of a one bulky group, energy requirement is slightly more. From 12.5, now we need how much? 14.2 to convert it into the eclipsed state. So there is some energy difference, right? Now in the propane, the energy difference is more than in the ethane, right? Now let's discuss about the conformational isomers of butane. And for the butane, we know that we have a formula of CH3, CH2, CH2 and the CH3. Okay, if I try to draw the energy, the conformational isomers around from C1 and C2 here, okay, between the C1 carbon and the C2 carbon, between this one and this one, you only get the two conformational isomers. Like the propane, this one will be considered as a one group. Okay, so around the C1 and the C2 in normal butane as well. Okay, in normal butane also, now what we have actually, we have a system like this now: hydrogen, hydrogen, hydrogen. This is the front carbon, the back carbon has two hydrogen atoms and it has a C2H5 group, right? Like in the propane, we had methyl, now we have ethyl group. So around C1 and the C2, you only have two, you can only have two the conformational isomers, staggered and the eclipsed one, right? You have two conformational isomers, staggered and the eclipsed. If I rotate it by 60 degree, what I get? From the staggered one, I get the eclipsed state, correct? I'll get the eclipsed one. And again, if you rotate it by 60 degree, what do you get? Staggered one again. So these are the two conformational isomers around the C1 and C2. But what about the C2 and C3 here? Between this carbon and this carbon, between the C2 carbon and the C3 carbon here. Okay, so now around this one you get different kinds of, more than two conformational isomers are possible, right? So if you look at this one, suppose this is the carbon number second, this is the carbon number second, and the circle one, this is the carbon number third. Front carbon, it has two hydrogen atoms and a methyl group. Suppose this is the methyl and the hydrogen. The C3 carbon here, this one, it again has two hydrogen atoms. Let's suppose it has two hydrogen atoms and it has a one methyl group also. Now the situation is a little bit different, right? Around C2 and the C3, you can have more than two conformational isomers. Around C1 and C2, you only have two conformational isomers, right? Let's try to draw the different conformational isomers of the butane around the carbon number 2 and the carbon number 3, right? Let's draw the different conformational isomers of butane around the carbon number C2 and C3. We have C1 carbon, the C2 carbon, C3 carbon and the C4 carbon, right? And here we have three hydrogen atoms, here we have two hydrogen atoms, here we have two, and here we have three hydrogen atoms. So let's find the conformational isomers around C2 and the C3. C2, suppose this is the C2 carbon, and C3, this is the C3 carbon here. Okay, and around the C2 we have got two hydrogen atoms and a one methyl group. It has a C1 is attached to the C2 it has 3 hydrogen atoms, it has 2 hydrogen atoms also here, and the carbon number 3 here, it has 2 hydrogen atoms and the 1 methyl group. So it has 2 hydrogen atoms and a 1 methyl group. Now what actually is this? This is called as a staggered, or this is also called anti, right? This is an anti-conformation. If I rotate it by around 60 degrees, 60 degree angle, so I think you get, suppose let's suppose I rotate the back carbon, and now you'll get it like this, right? It will move here, it will shift here, and it will shift here. Now there will be an eclipsion, isn't it? I think there will be an eclipsion, but the eclipsion will be between the methyl and the hydrogen, right? Here is the eclipsion between hydrogen. Here is the eclipsion between the hydrogen and the methyl, right? The CH3 and the hydrogen. Here will be the eclipsion between the hydrogen and the CH3. Okay, this is eclipsion, right? Again, if I rotate it by 60 degree, correct? This is the eclipsed state. Okay, now you rotate it by 60, again the same methyl group now will shift here, right? Okay, fine. We keep the front carbon groups at the same position, right? Will not change the front carbon. I am only rotating the back carbon one, right? We had the methyl here. Initially it was the methyl here, now the methyl in this one is here. Now the same methyl, it will move over here, so that means you get a methyl group over here. CH3 will be here, and this hydrogen will be here, and this one will be here, right? So it will shift like this, right? So you get a hydrogen here, you get a hydrogen here. Now this is not an eclipsed, this is not anti. We do not have the two methyl groups opposite, right? In this one we have the two methyl groups opposite, right? These two groups are actually in opposite direction here, at a 180 degree angle. Here is the 180 degree angle, but now here in this one, this is eclipsion, right? But now over here, this is not as eclipsed, not an anti, right? This is called the gauche, right? This is called the gauche conformation. Okay, fine. So if I rotate this molecule, if I rotate it again by 60 degree angle, what do you get? I think now the methyl and the methyl will be under eclipsion, right? The two methyl groups will be under eclipsed state. Now you have the front carbon with the methyl group, hydrogen, and then if I eclipse between the methyl and the methyl, now two methyl groups are under eclipsed. Here two hydrogen atoms are under eclipsion, and this one under eclipsion also. This is also eclipsed, but how is different than the previous eclipsion? In this one, there is the eclipsion between the hydrogen and the methyl. Here is the methyl eclipsion, right? The size of the two methyl groups is more, right? Here is the methyl group and the hydrogen. The size difference is less, correct? So that's why we call this eclipsion as a partial eclipsion. Okay, that's why we call it a partial eclipsion. So this is a partial eclipsed state, while this is fully eclipsed state, right? And in terms of energy level diagram, the most stable one is the first one. The anti is the most stable, right? So that is the most stable one. This is the most stable, because here the two methyl groups are far away. The distance is more, so the steric repulsions will be less. And the least stable is the fully eclipsed one, right? Okay, this is the least stable one. Okay, why it is least stable? Because there is an eclipsion between the methyl and the methyl. Okay, so that means if I give the ranking, the numbering to this one, I think the most stable one will be this one. Okay, and this will get the 4. Out of the 4, you get this is the fourth one, right? And the third one, the second one will be the gauche, right? Here is the gauche, and there is the eclipsion, partial eclipsion. Both are eclipsed, but this one is highly unstable than this one. The partial eclipsed is, you can say, relatively it is more stable than the fully eclipsed. So this is the third, this will be the number 3, and this will be the number 2 here in terms of energy, correct? So the most stable one is anti, then the partially eclipsed, then the gauche, then the fully eclipsed, correct? And if suppose if I rotate the fully eclipsed by 60 degree, what do you get? You again get this one back, the gauche. Now the methyl group here, it will shift over here, right? In this one you have the 2 methyl groups from this side. Now if you rotate it further by 60 degree, you get a further gauche. Clear? Okay, so you again get the gauche. These are the 4 conformational actually isomers. These are the 4 conformational isomers possible for the butane around the C2 and the C3. Around the C1 and the C2 we have found that there are only 2 conformational isomers possible, but around the C2 and the C3 there are 4 conformational isomers possible. Anti, which is the most stable, partially eclipsed, then the gauche, then the fully eclipsed. And if we look at the energy level diagram, it will look like this one. If suppose this is an anti here, the most stable one, okay, and if I rotate it by suppose here, if I rotate it by the angle of rotation is, suppose here we have an angle of rotation, okay, angle of rotation over here, suppose it is 60 degree. So what you get from anti, you get partially eclipsed, right? Partially eclipsed. In the previous slide we have discussed that, right? You can see here, okay. So by a 60 degree rotation, anti becomes partially eclipsed and partially eclipsed becomes gauche, right? And then you get the full eclipsed. So it's like this: anti, then partially eclipsed, and then further rotation around 60 degree. Further rotation by 60 degree, what do you get? You get the gauche, right? Isn't it? So the total is 120 angle of rotation here, isn't it? So the change here is 60 degree, correct? So you get the gauche, okay, and you further rotate it by 60, that means around 180 degree total rotation. So what do you get? This is anti. So this is not, this is the fully eclipsed, right? This is fully eclipsed, okay. So again you rotate it by 60, you get the gauche. You again get the partially eclipsed, right? Okay. So fully eclipsed, you rotate it by 60, you get the gauche, correct? So these are the different conformational isomers of the butane around the C2 and the C3 carbon, right? Okay, and hope you got the concept. Thanks for watching the video. Bye for now.